All right, everybody. Our last lesson on glaciers today. So last time we left off with erosional features of glaciers, mostly alpine glaciers, valley glaciers. Today we're going to focus on continental glaciers, and first how they've changed the landscape, and second, briefly we'll discuss why they actually grow so large in the first place. So here we have a nice continental glacier photograph. Let's move right on. Now, continental glaciers, remember, these things are huge. They cover continents, and that's why they're called continental. We're talking, the size of Greenland, the size of Antarctica. They tend, because of all the weight that they have, to round or smear the land, while valley glaciers sharpen it. Valley glaciers, you can think more like knives cutting through the landscape, and continental glaciers are just covering it all up. Now, in this area, continental glaciers have created features like the Great Lakes, the Finger Lakes, and countless small kettle lakes and swamps in the Adirondack Mountains. Here we can see the most recent glaciation in the lighter colored brown, and it has covered pretty much all of New York State with one exception. There's this small area in southwestern New York which was not glaciated. We have no evidence there of glacial extent, and it's kind of odd that that happened. I don't really know why. Maybe somebody does, but I don't. And this picture is a little more complicated. It shows the last 4 ice stages during the Ice Age: the Wisconsin, the Illinoisan, the Kansan, and the Nebraskan stages. And each stage, the ice advanced forwards and then hung out for a while and then retreated backwards. And once again, we have this interesting area, never glaciated, the driftless area in Wisconsin. Who knows why? Nice series of diagrams here showing 14,000 years ago, ice covering up much of the Great Lakes. 9,000 years ago, it starts to retreat and melt backwards as the climate changes for the warmer. And 7,000 years ago, even more. 4,000 years ago, we have the Great Lakes almost as we see them today. Now, back in the previous lesson, we learned how glaciers leave striations in the bedrock, these scratches. And you can see these dark lines. All these dark lines show the orientation that the ice was moving as it grew in this area. And we know pretty much that when ice moves, it's going to be moving from a colder place, an area of high latitude in this case, towards lower. And so you can get an idea, at least around Lake Ontario, that the ice flowed south or southeast away, in that general direction from the north. The Finger Lakes. These are 11 long, narrow, roughly parallel lakes oriented north to south, kind of like fingers. The southern ends have high walls cut by steep gorges. And these Finger Lakes, are a telltale sign. They're very deep, very narrow. They grow a lot of grapes here to make wine because of the water so deep there and kind of moderates the climate. But these wouldn't be here without glaciers. All right, some continental glacier depositional features. Just like valley glaciers or alpine glaciers, continental glaciers also leave moraines. They also, because of their tremendous weight, smear the landscape, forming these kind of upside-down spoon-shaped hills called drumlins. We have some in this area. There's a lot more south of Lake Ontario. Kettle lakes. These are large, buried ice blocks. When the ice was melting back, we think that the ice would block off and melt and leave depressions, which would fill up with water, and these became some of the ponds in the Adirondacks. And the outwash plain, deposits made by streams after a melting glacier. And remember, this area is once again sorted. The rocks are sorted because water carried these rocks, not ice, and layered or stratified. So here we have glacier deposited sediment on the left, surrounded by and that's unlayered and unsorted. And then on the right-hand side here, we would see sorted sediment because of the glacial stream melt-off, melt water runoff. Looks like braided streams on the right. And this is a great way to kind of figure out where glaciers stopped moving. You look at that line which separates the two, where you have the unsorted sediment to the sorted sediment. And that can also give you an idea of how far glaciers advanced forwards or advanced towards the south. You look for that line dividing the two types of sediment. This picture's loaded. It's got all kinds of cool features here. From our moraines to our drumlins, our kettle lakes, some glacial streams. Looks like a moraine-dammed lake. The outwash plain is below that terminal moraine. That's where water carried things and sorted it versus ice. Eskers, these where glacial, subglacial streams flowed and carried sediment. They kind of like these long, sinuous mounds of till. That's kind of cool. And these are features that you should be aware of. We'll talk more about after the video. This is a drumlin, a great picture of a drumlin taken from, looks like an airplane. And you can definitely see how it's steeper on one side than the other. This left side is a steeper slope and it's trailing off on the right. This actually shows direction of movement. We know that the glacier actually came from the left and moved towards the right. Now I wish these pens that I drew didn't have arrowheads on them. I can't seem to turn that off until I get Windows 7. But you get the idea. They move from left to right in this picture. In that direction. Here's a drumlin field in New York State. You can see these areas where there's pine trees. Farmers don't farm up the drumlins. They farm in between the drumlins, and so the trees are left behind. And they are oriented in the direction the ice went. Now, a side view or profile of a drumlin we already know about. We saw it in the photograph, and there it is, kind of like the upside down spoon. But a top view on a topo map would look pretty obvious too. You'd see a much steeper slope here where the lines are close, and then much farther apart would be the contour lines on the other side. And here's another one. So you get the idea. Drumlin fields produce these very odd-looking hills. And questions, pretty obvious answer for this question because we're just talking about it. But it represents the side view of a hill that was deposited by a glacier in central New York. The hill is most likely composed of, and we're looking for stuff that glaciers leave behind, which are unsorted sediments. Ice doesn't sort, it just drops them randomly. Long Island, a series of moraines, like the Ronkonkoma terminal moraine, the Harbor Hill recessional moraine. And you can see it's not just Long Island that has these moraines, terminal moraine and recessional moraine, but Martha's Vineyard, Nantucket, Cape Cod. These are all places that were glaciated. In fact, a lot of them wouldn't be there if the glaciers didn't dump all that sand and gravel behind as they formed and then melted. Thanks to Charles Burrows for this. Shows the ice advancing forwards, leaving the Ronkonkoma moraine. And up to 70,000 years ago to 45,000 years ago. This is the Wisconsin Glacier. As it retreats, the melting ice formed the outwash plain along southern Long Island. And there's your Ronkonkoma moraine. Then another advance, about 20,000 years ago. And this formed the next moraine, the Harbor Hill moraine. And then as the climate gets warmer, it retreats backwards, leaving it behind as well. So now we have two moraines. And now, wave erosion, beaches form. The landscape starts to change into what we now see today. Cool video. Thanks to Charles Burrows. All right, here we have some glacial outwash deposits. In New York State, we actually have a pretty big economy for high quality sand and gravel because of all this glacial action here. So it's a valuable resource. I know there's a few quarries right in this area, not within a 10-minute drive from here. And thanks to Glaciers, people make a living off selling this stuff. All right, some glacial history. Here we can see 2 million years ago on the far right, the Nebraskan stage, then an interglacial when it's warmer, and then it gets colder again in the Kansan stage, and then warmer, and then colder in the Illinoisan stage, and then in the interglacial it's warmer, and then the last ice age, the Wisconsin, is what shaped what we now see in New York State, most of that, and now we're in another warming period, as you can see by the graph right there with temperatures. So there's been many warming periods and cooler periods and warming periods, and there's no sense in thinking that it's not going to happen again. Of course it's going to happen again. The Earth's climate during the last 2 million years has been dominated by shifts between cold periods, known as ice ages, and warmer periods, known as interglacials. Here's another graph showing the warmer versus the cooler periods. And the far right-hand side of these graphs, where the peaks are on the right, those are glacial periods when it's cooler. And the far left are the interglacials. Today we are in a warming period, as you can see right there. 50,000 years ago, much colder. 130,000 years ago, much warmer. You get the idea. Earth goes through climate change. Same idea, different graph. From 250,000 years ago to today, you can see the temperature goes up, goes down, up, even higher, down, down. And when it's cool for a long enough period of time, these glaciers grow very large. And obviously now we're in a warmer than normal period, and the glaciers are melting back. Doesn't take much temperature to change that, though. Now, although there might be human-induced global warming, we also have to realize that the Earth does change temperature on its own. And this particular idea is called the Milankovitch cycle. And it has to do with changes in the tilt of the Earth's axis. The Earth's axis precesses or wobbles from about 21 to 24.5 degrees every 41,000 years. And the shape of the Earth's orbit does change as well. It becomes a little bit less, a little bit more elliptical, taking a little bit farther away from the sun on a 100,000-year cycle. And when you add up all these cycles, we get about a 100,000-year glacial cycle. About. Now this could obviously change a little bit. Since then, however, fears of global warming as a result of man-made greenhouse gas pollution have dominated the environmental agenda. It's hard to predict. We really don't know because we don't have enough data going back far enough. I mean, we can get a general idea, and we also, it's hard to understand how much effect humans are producing on climate. Only time will tell. We can only just, I guess, be safe than sorry. And I'm going to stop here instead of showing you this. This kind of blows things out of proportion in this particular applet, so I'm not too happy with it. But that's it for today, guys. Hopefully you understand a little bit about continental glaciers and how they've changed our landscape and why they form.